Alright, so this is our first go at this. We'll see how it goes. Acetone is leaked into a process building. An organic vapor analyzer indicated 7,800 parts per million of acetone in the air. The building has dimensions of 12.2 meters by 24.4 meters times 9.1 meters. And there was no general ventilation. The molecular weight of acetone is 58.08. Its specific gravity is 0.79. The temperature in the process building was 25 degrees C, and the barometric pressure was 101.3 kilopascals. How much acetone leaked from the tank, assuming complete vaporization? Alright, so we're going to write down everything that we know. We've got 7,800 parts per million. We've got a volume is equal to 12.2 meters times 24.4 meters times 9.1 meters. That's going to be 2708 meters cubed. We also know that for acetone, it's 58.08 grams per mole. And then we also have that the specific gravity is equal to 0.79. And we're at ambient temperature and pressure. So pressure is equal to 101.3 kilopascals. Temperature is 25 degrees C. Okay. This is not your easy plug and chug problem. There's a lot that's going to happen. So the first thing that we need to do is, how are we going to use this parts per million? Well, there's a formula, and we'll go over it later because it caused me a lot of grief for the last 2 days. But it says that if you have parts per million, and it's important to note that this is volume parts per million. And so what that says is you have 7,800 meters cubed per 1 million meters cubed, right? So another way to look at that would be 7,800 times 10 to the negative sixth meters cubed per meters cubed. Now normally you would cancel these units out, but you leave them like this because we're going to use that later. And that's how one of the ways that you arrive at milligrams per meter cubed is actually equal to your 7,800 times your 5808 grams per mole divided by 24.45 liters per mole. And these units don't cancel to make these units. And that's what caused all of the issues and why I spent 2 days on this problem. But anyway, I figured it out. so no worry. What you get when you work this out is that you have 18. Let's see, it's about 18,529 milligrams per meter cubed, okay? And what you can do now with this is multiply by the volume that we had up here to figure out how many grams of acetone are in that space. So we're going to convert this real quick to grams per meter cubed. So you have 18.5 grams per meter cubed because there's 1,000 milligrams in 1 gram, right? Next, what you're going to do is you're going to take 18.5 grams per meter cubed and multiply by 2708 meters cubed, okay? And that's going to give you 5,000 or 50,193 grams, okay? From there, you have that there are, you need to figure out how many grams there are per liter and work backwards from that. That's what you're going to use specific gravity for. So if the specific gravity is 0.79 and there's 1,000 grams per liter with water, it's H2O, and we know that specific gravity, I have to go to a new page. It's stuck. So, specific gravity is the ratio of the density of your substance, whatever it might be, divided by the density of H2O, right? So any relationship that we have as far as specific gravity goes, we can use to figure out the density of the substance. So if I have specific gravity of acetone, which is 0.79, and I set it equal to density of acetone divided by density of H2O. H2O, we know the density is 1,000 grams per liter. So if I do 0.79, I'm going to multiply both sides by the 1,000 grams per liter. Oops. And so it'll cancel here, and then I get equal to P of, or rho, acetone. Okay? Now I have 790 grams per liter is the density of acetone. Okay? That's all you're doing whenever you're using specific gravity. So now I go back here where I said I have 50,193 grams of acetone, and I can multiply, or sorry, we're going to end up dividing. So if I start with 50,193 grams of acetone. I'm going to multiply by 1 over the density of acetone, grams per liter. And what that'll do is that'll flip this upside down. 1 over any fraction inverts it, right? Creates the reciprocal. And so what that'll do is my grams will cancel, and now I'll just have how many liters of acetone I have. And once I've done that, I have my answer. Okay? What did we need to know to work this problem? Basically, everything you did in this problem was some sort of unit conversion, okay? We needed a way to get from parts per million to some sort of grams per meter cubed. Then we needed to get from grams per meter cubed to grams. And then we had to get from grams to liters. And then we had our answer, okay? So, what did we do to accomplish that? First, let's start with this equation that I guess they give it to you, maybe they don't, I don't know. It caused me a lot of headaches. It says that mg per meter cubed is equal to parts per million times molecular weight divided by 24.45. This number right here is your liters per mole under ambient temperature and pressure. So anytime the pressure is 1 atmosphere and the temperature is 25 degrees C. So basically your normal laboratory conditions. This is your parts per million in volume, and this is your molecular weight. Let's just start by how you get this number. Where does this number come from? So this number is from the PV equals in RT equation, okay? Pressure times volume is equal to the moles times the gas constant times the temperature, okay? Whenever we use this, it all depends on the R that we use. So whatever the units are of pressure, volume, and temperature that we're looking at, we need to make sure that our R is the correct constant for those units. Okay. The other thing is this is kind of a weird deal, but basically what you do is you say let N equal 1 mole, okay? And let V be what we're trying to find. So what that gives you is, you'll let pressure equal 1 atmosphere. And then temperature is going to be 25 degrees C, but you can't leave it in degrees C because then you would end up dividing by zeros, and that doesn't work. So that ends up being 298 Kelvin, okay? And the way you get from here to there is you say Kelvin is equal to degrees C plus 273 degrees, okay? So now, just using these units, we're going to plug everything in, right? So we said N is equal to 1. So now we're going to have PV is equal to RT. Now we're going to plug everything in. So what we get is 1 atmosphere times volume, which we're not going to find, times, I can't remember which R we're supposed to use. I'm going to have to look it up here in a second. R times 298. Okay. Let me look the R up. Pause it for a minute. All right, so I found it finally. So for R with the units, liters atmosphere per Kelvin mole, it is equal to 0.008205. Okay, so now we plug that in here. So we get V is equal to, we've still got our little mole out here because there's 1 mole. Don't forget that unit. And there's Kelvin right there. So V is going to be equal to, we want to divide by our 1 atmosphere, but it's just a 1. So really we're just going to move atmosphere over there. And you're going to get your 0.008205 times your 1 mole divided by your 1 atmosphere. There'll be 298 up here times Kelvin. And then you're going to put your units of R over here. So L atmosphere, K mole. So the mole will cancel. Your Kelvin will cancel. Your atmosphere will cancel. Okay? And then all we really got to do is multiply this 0.008205 times 298. And I'm having to do it on my laptop because my phone is the one doing the recording. So just give you a minute. And that gives you 2.445. That seems slightly off. Should be 1 decimal place over. I wonder if I put too many zeros in there. No, doesn't seem to be. What have I done wrong? Oh, there's one too many zeros in there. That one shouldn't be there. It should be 0.08205. So that would be 24.45 liters, right? And so that's how many liters of a gas you would have if you had 1 mole of gas at ambient temperature and pressure, okay? But this doesn't have the correct units to work up here, like we said earlier. So what do we got to do? Well, it helps, and then we're going to say this is liters per mole because we used 1 mole in there, right? And so we can add that back in by saying we're using 1 mole of substance, right? Or it's per mole of substance. So if you had 2, you just double the number, right? Now we got to get that to where we can use it. Okay. So 24.45 liters per mole. Okay. This right here, we can change that into meters cubed. There's 0.001 liters, I believe. No, there's more than that. 0.0001 liters per meter cubed, right? So a better way to write that, liters per meter cubed, right? So now we can stick that into here, okay? And what that's going to do is move the decimal back 1, 2, 3, 4. So then you're going to get 0.02445 liters per mole, right? Sorry, not liters. We just changed it to meters cubed, right? And so now, when we do our parts per million times 58. Oh, let's not do it that way. We're going to do, so we'll put our units in for parts per million, right? And what that says is it's going to be your parts per million will have units of 10 to the negative 6 meters cubed divided by meters cubed, right? So you're going to put it in 10 to the negative 6 meters cubed divided by meters cubed times, which you're going to put in your molecular weight, right? That's going to have units of grams per mole, okay? That's all going to be divided by this number that we just figured out, 0.00245 meters cubed per mole, right? But we can rewrite that as, so don't write it like that, write it as, need to make room, 24.45 times 10 to the negative 3 meters cubed per mole, right? And so now our new equation is 10 to the negative 6 meters cubed per meters cubed times grams per mole divided by 24.45 times 10 to the negative 3 meters cubed per mole, right? So the moles cancel, 2 of the meters cubes cancel, and what you get is this is kind of important, you're going to combine these. So if I have an exponent, we'll work this off on the side. If I have something to the negative third, or sorry, say we have something to the negative 6 divided by something to the negative third, it's equal to a to the negative 6 minus negative third. And what that ends up being is negative 3. So we get 10 to the negative 3 divided by 24.45 meters. Well, those units went away. Grams per meter cubed, right? So 10 to the negative third times grams, you can lump those together and that turns into milligrams because there's 1,000 milligrams per gram. So if I absorb that into the unit, it becomes milligrams. Don't think that you have to understand all of that. I just had to do it because it bothered me. Because I don't like it when you just see an equation where units don't match up. And that's a lot of units work, and it's kind of a robust subject. But this is the simple thing with units, right? If I have some quantity A that's in liters per meters cubed, right? And then I have some conversion factor for A that says, A's density. So density is usually rho. So density of A is equal to however much grams per liter, right? Because density is mass divided by volume. I can take A times density of A, their units, meters cubed, grams per liter, and the liter will cancel out, and now I will have some quantity B that's in the units, grams per meter cubed, okay? That's all we're doing. We're just trying to move things around to get a number that's useful to us, right? Then say I had a volume. So I can take this quantity B with grams per meter cubed and I can multiply it by a volume that has units of meters cubed. Now the meters cancel, and I know how many grams of B I have, or grams of A that I have, right? So you get B times V grams, okay? The other thing that was kind of important that we went over is, what do you do when you have a number with an exponent, say x to the a power divided by x to the b power? Since x and divided by x, they're the same term, right? So that's going to equal a to the a minus b. What if it was times each other? So I have x to the a times x to the b. Then you add them, x to the a plus b, okay? The only time that this works, though, it's just like fractions, division and multiplication, right? If I'm trying to add a, or x to the a power plus x to the b power, they remain the same. You can't do anything with that. It's still x plus x to the b. But I could factor an x out. So I could factor out x to the a, and then you would get 1 plus x to the b minus a, okay? But that's all you can really do with those. Very similar to some of the rules that you have with fractions, all right? What else did we need to know? That's about it. Call it good.